Okay, yeah, so we are going to conclude the lectures with this final one about adoption issues and how to enable the adoption of processing in memory in real systems. We are going to discuss different issues that still need to be tackled or are being tackled in order to make processing in memory a reality in computing systems, in real world computing systems. There are the different potential barriers. I think that over this slide Onur went this morning, but we can recap very quickly on it. Like applications and software for processing in memory. This is one of the barriers because we basically need to identify what are the workloads, what are the applications that can benefit from processing in memory, and also we need to create new software for those processing in memory systems. And this connects to another important point that we will later discuss a little bit more, which is the ease of programming, interfaces, compiler, and hardware support that is needed for processing in memory systems. Because in the end, that's going to be, I mean, every time you have a new device and you need to learn how to program the new device, there is a learning curve, and this makes things a little bit more complicated. Then we need system support, we need security support, features like memory coherence, synchronization, virtual memory, isolation, communication interfaces, and all of this needs to be tackled, as well as runtime and compilation systems that allow adaptive scheduling, data mapping, access sharing and control, and also infrastructures that can be used to assess the benefits and the feasibility. Infrastructures like, for example, simulators or real-world prototypes, as the PIDRAM thing that we presented before Manuel's talk, but also workloads, benchmark suites that can be used for different studies related to processing in memory. And all these issues and all these barriers can be solved with a change of mindset, and these should also or requires us to also revisit the entire computing stack from the problem and the algorithm to the devices themselves. So, but we can go step by step and fulfill all the needed changes and modifications of the real systems. Most of these different points are discussed in the corresponding section in the book chapter that we wrote, and we keep updating from time to time, and it's publicly available in archive. Actually, section 8 is about enabling the adoption of processing in memory. You can also read shorter versions of this book chapter, like, for example, this one that was presented in published in MicPro 2019, and also this other one in the journal, in the IBM Journal of Research and Development. So one of the things that are necessary to enable the adoption of processing in memory are real prototypes. I mentioned the PIDRAM prototype earlier, but also the real PIM systems and prototypes that we have discussed today in the morning. We talk about ABMEM, we have talked as well about FinDRAM from Samsung, or AIM from SK Hynix, these other proposals from Samsung, AXDIM, HBPNM from Alibaba. We have had a very interesting talk by Diming, and for sure there will be more to come. Something that was recently announced by Samsung, for example, is this experimental platform with an AMD GPU with HBM PIM memory, and they have demonstrated really interesting improvements, like around 2 times energy savings and 2 times performance improvement compared to a baseline system where the HBM memory, or a baseline GPUs where the HBM memory is not PIM enabled. And I think, and I also mentioned it in the initial slide, that efficient interconnects that allow communication for the different devices are also necessary to make processing in memory more accessible to everyone. I think that the Compute Express link industry is now developing is also very promising in the context of processing in near memory. And in that sense, there have also been some recent announcements from Samsung where they have shown this CXL controller with some PNM processing near memory capability that is not clearly specified in their post, but you can read it by yourself. The thing is that it's, there is going to be a combination of processing near memory or processing in memory systems in or architectures in different parts of the system, and hopefully this can be really beneficial to tackle the data movement bottleneck and alleviate this classical problem. Another of the barriers that need to be solved with respect to the adoption of processing in memory is how to program these architectures, how to generate code for them. Here in this tutorial, we have been talking about how to program the AppM PIM architecture, and we will be talking about how to do it right after the coffee break, because you are going to have the chance to work with the real system. And we have also discussed how to program processing using memory systems like the SIMDRAM one, how to create new instructions that can be executed using DRAM, and how to write programs for this. But still, every time we have a new device, we need to learn how to program, and that's a steep learning curve that we should soften as much as possible. So hopefully there will be more and more programming frameworks, high-level programming frameworks that allow us to create code for processing in memory systems. But for that, we will need good IR, and we will need also good compilers that can do that. I think that there is some good work to come in the next few years. This is a lecture about SIMDRAM, by the way. I should have shown this earlier for sure, but if you want to go in depth over this SIMDRAM framework, you can check this presentation. Runtime as well, when to schedule and how to when to schedule computation onto the PIM system, and how to map data onto the PIM system. This is something that has been, I mean, it's covered by many different works. Like for example, in our group, we have these PIM enable instructions that basically propose to offload simple computations, simple operations to the memory side. Here you have the example of the PageRank algorithm, where you know, in the typical execution in a conventional architecture, there is a lot of data movement, cache lines going back and forth between the main memory and the host processor, because in the end there is not so much computation in this algorithm, and the accesses tend to be pretty random, so there is not so much temporal locality of the cache lines that are brought to the processor. So what this work proposes is to offload simple operations, like for example this PIM add, to the memory side, and this way save a lot of data movement, basically moving only 8 bytes to the memory and then computing. This work also proposes an intelligent scheduler by using this locality monitor that can check whether a cache line, the cache line that you're going to operate on, is in the last level cache, or is, I mean, is in any of the levels of the cache hierarchy, or is in the off-chip memory. By checking this PIM directory, the locality monitor can figure out if one cache line is near the host, near the CPU, or is in memory. And based on that, schedule the computation onto the corresponding compute unit. This PCU near the host processor, or this PCU near the in the logic layer of 3D stack memory. The PEI work showed very interesting performance improvements for large data sets in this case, that can be even better when scheduling properly. That's these lighter green bars represent the results for the locality aware execution. And here you can see also some energy consumption results that also show that the locality aware approach produces better energy efficiency. And this is the paper that was presented at ISCA 2015. But it's not the only work that has tackled this idea of scheduling at the right time and in the right device. For example, this other work about processing in memory for GPUs needs to deal with proper scheduling, identifying pieces or parts of a GPU kernel that are good for execution in compute units here in the logic layer of 3D stack memories, or in the regular cores in the main GPU. And such a proposal requires also to properly map the code and also properly map the data to the right place, because you don't want to offload something to the cores near the memory or the cores in the logic layer and then have these cores having to access another stack, right? So it's important to have efficient mechanisms for data code mapping and for data mapping. You can read more about this one in the Tom paper that was presented in ISCA 2016. And there are other papers, like for example, these scheduling techniques for GPU architectures, which has a similar purpose, but relatively different approach, performs more coarse-grained offloading of the kernels to the either the regular GPU cores or the processing in memory cores. And there are more like, for example, this one, accelerating dependent cache misses, or this continuous run ahead that do some sort of processing in memory near the memory controller. So there are many research questions to still answer, or to answer for the different devices, the different processing in memory systems that we will see. What are, for example, what are simple mechanisms to enable and disable PIM execution? How can PIM execution be throttled for highest performance gains? And how should data allocations and access patterns affect where or whether the PIM execution should occur? Other questions like which parts of a given application should be offloaded? How do we identify those parts of an application that are more suitable for processing in memory? And when do we schedule, right? So maybe some particular part of the code is potentially good for processing in memory, but maybe not all the times, depending on where the involved data, the involved cache lines are at a given time. And also scheduling mechanisms for multiple programs. For I mean, you may have multiple cores requesting access to the PIM system, but also multiple workloads requesting access to the PIM system, right? So I think there is still a lot to do in that direction to enable multi-core systems to access processing in memory units, and also to enable multiple workloads different workloads to share the access to processing in memory. Memory coherence is also an important issue that requires efficient solutions. And in that sense, we have shown in prior work that traditional coherence mechanisms, like, for example, fine-grained coherence mechanisms as a MESI protocol can be, or coarse-grained mechanisms, or maybe even non-cacheable areas of memory, they don't really provide as much. I mean, they don't really allow us to get the best or get the most of an ideal PIM system, as you can see. Or past work, lazy PIM, and the follow-up work conduct propose an efficient coherence mechanism for near data accelerators or for processing in memory architectures. Let me very briefly go over the ideas in this conda, lazy PIM, and later conda work on how to maintain the coherence between the PIM side, or the near data accelerator, as it's called in these slides, and the CPU. The basic, there are some key observations in order to enable these coherence mechanisms. First of all, these mechanisms eliminate a significant portion of the NDA's benefits, of the PIM benefits, as we have seen in the initial slide with this results for different coherence mechanisms. The majority of chip coherence traffic is unnecessary, and much of this coherence traffic can be eliminated with a coherence mechanism that has insight into the memory accesses. So the Conda paper proposes an optimistic approach. First of all, gain insights before any coherence check, and second, perform only the necessary coherence requests. Basically, this optimistic execution of loads or allows the offloading computation to the processing in memory side, start the computation on the processing in memory side, and just let both the CPU and the processing in memory side compute in an optimistic manner as if there were no coherence issues. But at the end of the section that is executed on both sides, a signature is created. This signature records the cache lines that have been accessed by both sides. So what the NDA side or the PIM side does at the end of the execution of this code section is to return the signatures to the CPU, and the CPU will check if both sides have by chance accessed the same cache lines. If that's the case, then we will have to re-execute, but if it's not, then we are done. We can commit and we can continue with the execution. The good thing of doing this is that we are saving most of the coherence traffic, and we can be much closer to the to an ideal coherence mechanism, as you can see in that banner. So this is the Conda paper presented at ISCA 2019. Important and necessary as well, synchronization support, because processing in memory systems are typically distributed systems where we have multiple cores. We may have thousands of cores, as is the case of the admin PIN system that we have covered in the morning. In this sense, we have very good work presented a couple of years ago at HPCA, led by Christina, who was one of our invited speakers today. It's Synchron, efficient synchronization support for near data processing architectures. And what Synchron proposes is a hardware-based synchronization mechanism that is suitable for processing in memory systems. As you will see, it provides very interesting results close to the ideal zero overhead synchronization scheme. Synchronization is necessary for sure in any system where we have multiple threads running, computing on the same workload. For example, in this single source shortest path code, you can see that there are some vertices that are being visited, and the distance to the neighbors is being updated in every iteration of the algorithm. And if we have multiple threads visiting these neighbors and updating the distance to these neighbors, we need to lock the access to the, in this case, the distance array. So how do we enable this sort of lock mechanism or this sort of mutexes for this application and also for many other applications as the ones that you can see on the slide? We are going to discuss that. So for the baseline NDP architecture, we consider an NDP system that is composed by multiple NDP units, and inside each of the NDP units or PIM units, we have multiple NDP or PIM cores, as you can see. Each of them have their own private cache, may have their own private cache, and they by themselves are an accelerator or a programmable core. And they have shared access to the same local memory that is called main memory here for each of these NDP units. Challenges when implementing synchronization in NDP systems. First of all, the lack of coherence support. We have discussed, or we have just talked about coherence support in the in Conda, but this coherence support is between the CPU side and the processing in memory side. Here we are talking about no coherence support between the different cores that take part of the PIM side, right? So for example, in the admin PIM system, there is no coherence support at all. All memory coherence need to be handled by the programmers. The idea in this work in Synchron is to propose a synchronization mechanism that can work transparently for the programmers. But there are challenges. As I said, the first one, the lack of hardware cache coherence support. the expensive communication across NDP units, and the lack of a shared level of cache memory. There is no shared memory space by all processing in memory cores. So that makes that, first of all, traditional synchronization mechanisms like shared memory base cannot be used. So we have to go for message passing mechanisms. We could go for a software-based scheme, but it's going to be way more overhead. So that's why the Synchron paper proposes a specialized hardware support. And here you can see basically what are the basic ideas. For this hardware synchronization support is to have a synchronization engine, a small synchronization accelerator inside each of the PIM units, so that the PIM or NDP cores can send the requests to the local synchronization engine, and these different synchronization engines in different NDP units can interact and communicate as it's needed. If we look at the internals of the synchronization engine, we will see that there is a synchronization processing unit, synchronization table, and indexing counters. So every time that there is a request from one of the cores, for example, a lock acquire operation, the one entry in, so the lock operation creates a new entry in the synchronization table. Observe that here it's an operation that is low latency because it doesn't require memory accesses, because the synchronization table is an SRAM table, SRAM-based table that resides inside the synchronization engine. And then Synchron support hierarchical communication. Usually we are going to designate a master synchronization engine, that is the one that is closer to the synchronization variable in this case. And the hierarchical communication is going to work in a way that inside the NDP unit, the different cores send the request to the local synchronization engine, and then this local synchronization engine sends a single request, a global lock acquire in this case, to the master synchronization engine. This hierarchical approach minimizes the synchronization traffic, as you can see. So Synchron is the first end-to-end synchronization solution for NDP architectures. Benefits such as high system performance, low hardware cost, programming ease, and a general synchronization support. And it comes within 9.5% and 6.2% of the performance and energy of an ideal zero overhead synchronization approach. So yeah, this is the paper. Here you can find a link if you want to find all the details of this work, as well as some talks that Christina has delivered. For example, this one was in one of the editions of our processing in memory course. How to design data structures for processing in memory as well, concurrent data structures such as skip lists, linked lists, or FIFOs. They also, I mean, we also need to be really careful when designing these sort of concurrent data structures for these kind of systems, and it's related as well with the synchronization issues. And virtual memory support. This is, I think, also one big issue for, to enable processing in memory that it's yet to solve, and it's likely that the right solution for different processing in memory architectures and different devices will be kind of custom for the specific characteristics of the processing in memory system. For example, if you have something as simple as PIM enable instructions that I introduced a few slides ago, where we are just operating on a single cache line, it's likely, well, and actually what the paper proposes is to perform the address translation in the host and just directly send the request to the corresponding PIM unit that is going to execute the PIM enable instruction and operating on a single cache line. If the processing in memory core requires, has access to a larger memory space and needs to use many different cache lines, we might need more complex solutions. In this work, for example, accelerating pointer chasing in 3D stack memory, it is proposed pretty interesting mechanism for to support virtual memory that is based on the use of let's say, custom page table for the processing in memory accelerator. The work bases the solution in two different techniques. The first one is the page table, the IMPICA page table that I just mentioned. The second one is the address access decoupling, so that we can exploit parallelism and we can concurrently calculate addresses, perform the virtual memory address translation, and at the same time perform memory accesses to the 3-stack memory for whatever pointer chasing operation we need to carry out. Like, for example, leaked data structures that, as you know, are very much used in different important applications like databases, B-trees, key value store, hash table, etc. So they are connected by pointers, and here is the issue with these kind of applications when they run on a CPU, is that for every single every single pointer chasing operation, when traversing, for example, this tree, we need to go to memory with one address, fetch some data, obtain a new address, then go again to memory, fetch the data again, and so on and so forth. And this requires a lot of back and forth between the memory and the CPU. So the basic idea of this IMPICA work is to create or embed an accelerator for pointer chasing in the logic layer of a 3D-stack memory, and let this accelerator perform the entire pointer chasing operation from this H to this A, so that everything is done in the logic layer, and just the final data that the CPU needs is returned to the CPU, to the host processor. But there is, I mean, one issue with doing that. If you have a single CPU core, you have a single thread, because the memory access is going to be faster, being closer to memory in the in-memory accelerator reduces the latency. You can save time, that's for sure. But as soon as you have more than one core, you have multi-threaded execution on the CPU, and you can parallelize computation and parallelize memory accesses, you completely lose this advantage, right? So it's slower for two operations when the CPU has more than one core. So that's why the idea is to decouple the address calculation and the memory access. And that's why the IMPICA accelerator proposes an address engine and an access engine, so that the address engine computes the address, gives it to the access engine that performs the memory access, and while the access engine is accessing memory, the address engine can continue computing new addresses. And this way, we can save, again, time with respect to the execution on the CPU. And this is a basic figure that illustrates how to perform these operations. First of all, the requests go to the address engine that calculates addresses and queues these addresses for the access engine to read them and access the data in DRAM through the memory controller. But now we need to perform this address translation, right? And if you do it in the way a CPU does it, this requires multiple page table walks, and in the end, multiple memory accesses that make all these operation very costly. So because in principle, there is no memory management unit on the memory side, and duplicating it would be extremely costly, the IMPICA paper proposes the IMPICA page table. That is a reduced page table that only only spans a small part of this IMPICA region of the virtual address space. From there, it's like from a small region to any physical, so to any address in the physical address space. And but at least this way we can have a much more lightweight page table, thanks to this region table that is very small, because remember the in-picker region in the virtual address space is very small. This region table is usually going to stay in the cache of the processing in memory accelerator, and the flat table, so this is the tiny region table, is always in the cache, while the flat page table saves one memory access with respect to the traditional page table works. So by doing that, we can have a more efficient mechanism for virtual memory address translation. And here you can see some results from micro benchmarks with linked list, hash table, and V3, and some interesting speed ups for the in-picker accelerator with respect to the baseline. And also here, some results for database performance, and also like up to 16% higher throughput and 13% lower latency. And for energy consumption, also some interesting energy savings. And here you see also some values of area and power overhead. So if you want to check all the details, you can go to the paper that was presented in ICCD 2016. As I said, it's likely that the virtual memory, or the solutions for virtual memory address translation will be custom for different processing in memory systems, depending on where they are integrated, whether CPUs, GPUs, etc. But there is also some good recent work from our group that can be potentially adapted, can be potentially suitable for processing in memory systems as well. This virtual block interface that allows a lot of flexibility when performing memory address translation by offloading or by placing the address translation capabilities in the memory controller. This is a lecture about the virtual block interface if you are interested in learning about it. Processing in memory has also security implications, that's for sure, and it's something that needs to be researched as well, but it can also provide interesting security mechanisms or interesting primitives that can be used for security mechanisms. For example, in our group, there is a lot of interesting work on creating physically unclonable functions in DRAM by playing with the latency, by reducing the latency parameters in DRAM, and this way creating the paths by taking advantage of the random process variation of the DRAM cells. So by accessing at a reduced TRCD, is possible to obtain these paths. This is work that was presented at HPCA 2018, and based on a similar idea, DRange, presented 1 year later, also proposes a way of obtaining random numbers. More recent work also to obtain true random numbers using DRAM is this quadruple activation, this QUAC TRNG work that is kind of based on similar ideas to the ones in the compute DRAM work and PyDRAM work that I presented in the beginning of this session. By violating the timing parameters, is possible to activate 4 rows. We have seen 3 rows in the compute DRAM work. We realized in this QUAC TRNG work that it's possible to activate 4 rows with 2 activate commands. And if you have 4 rows, and these 4 rows have a pattern like this, 1, 0, 1, 0, and you activate these 4 cells at the same time, what will happen is that there is random behavior at some point. So observe that we first activate row 0, then pre-charge, then activate row 3, and because these 4 rows start sharing their charge with the bit line, at some point when the sense amplifier is enabled, you don't really know where the voltage is going to go. So that's basically a random perturbation that gets amplified, and based on that, it's possible to obtain random bits inside the DRAM. That's the idea, that the basic idea that the QUAC TRNG work exploited obtaining these random values or these operations that reduce latency as a source of entropy. And then, well, these random values are later post-processed in order to obtain true random numbers. Yeah, and here you can find the link to the paper. And more things that I mentioned in the beginning that we need in order to continue with the research on processing in memory and enable the adoption of PIM, simulation infrastructures and benchmark suites. And we have done quite a bit of work as well in this direction, related to the work, the characterization work that we did of the UPMEM PIM architecture. We produced this PIM benchmark suite that is composed of 16 different benchmarks, as you see, from different domains like dense linear algebra, sparse linear algebra, databases, graph processing, neural networks, etc. They are publicly available in our repository, and yeah, we have talked about them extensively in previous talks. But not only those, because those are, you know, like designed for the UPMEM PIM architecture. If you want to go more general, here in this DAMOVE work that was also published recently, we propose a methodology to characterize workloads and understand how good or bad they can be for processing in memory. And DAMOVE also comes with a benchmark suite that is, in the end, all the many workloads that we analyzed to came up with this methodology. I think that there are more than 100 different workloads that are coming from different benchmark suites, popular benchmark suites like SPEC, Parsec, etc., Parboil and Rodinia, and many more. And we put them all together and we analyze and identify what functions in these workloads, in these benchmarks, can be more or less suitable for processing in memory and due to what reasons. That's how we came up with this methodology that performs application profiling, and then by using the DAMOVE simulator, does further analysis, locality-based analysis, and also memory bottleneck classification. In total, we found that there are 6 different classes of workloads with respect to their data movement needs, and most of them can benefit from processing in memory in one way or a different way. Here you can find links to the paper, to the repository, the simulator and the benchmark suite, and also a couple of links to talks or lectures given by Geraldo, who is the PhD student, who is the first author of this work. Here you can see one of them. Okay, and I was talking about simulation infrastructures. I mentioned the DAMOVE simulator. The DAMOVE simulator basically integrates SetSim that allows us to simulate in order or out of order cores, and is integrated with Ramulator, that is a DRAM simulator that has already been used by created in our group and used by people in our group for many years, and also in other research groups in academia and industry, as you may know. And there are also other simulators that can potentially be used for processing in memory. For example, this MQSim for modern multi-queue SSD devices. And in terms of characterizing workloads and understanding how suitable they can be for processing in memory, I just mentioned the DAMOVE methodology, but we also have some work that is based on ensemble learning to make a prediction of what's the performance of a workload on a specific processing in memory system. The good thing of this NAPL approach is that it can save a lot of exploration time with respect to using simulators. Basically, when you use simulators, you need to spend a lot of time on running simulations, and that's, as you see, well, thousands of times slower than native execution or execution on a real system. So that's why we propose this NAPL model that is based on ensemble learning. It has, first of all, we need to train the model, then we can use this model, and the model is based on extracting characteristics from the application and also characteristics of the architecture itself you put them all together in the ensemble learning algorithm and come up with the model generation that that can be later used for performance prediction, performance and energy prediction. And well, we evaluated these extensively for a bunch of workloads, compared them to other approaches to do basically the same sort of estimates, like a decision tree or an artificial neural network, and in the end, we observed that the error in the performance and energy prediction of NAPL is significantly better than the other approaches, and also significantly faster than using simulators. And then one more thing, applications that benefit from processing in memory and optimized implementations of applications that can benefit from a specific processing in memory systems. In that sense, in our group, we have done a lot of work in, for example, genomics, like this green filter that proposes a way of filtering reads in genome sequencing, doing it inside or near the memory with 3 stack memories, but also how to accelerate, approximate string matching, and how to accelerate sequence alignment has also been thoroughly studied and discussed in these papers. Like, for example, this GenAsem that proposes a new algorithm to perform sequence alignment, and also an acceleration framework, near data acceleration framework, that really produces very good performance results. Other workloads that were mentioned as well by Onur this morning, like Google workloads for consumer devices. I think Onur also talked about this Nero accelerator for weather prediction modeling using near data processing as well, or this NATSA accelerator for time series analysis, which is also like a very memory-bound, memory-intensive application that can benefit from processing in memory. And these are just a few examples of these applications for processing in memory. Just as the epilogue to this lecture and say the lectures of this tutorial, recall that we have a very nice summary of many different works in this modern primer of processing in memory, this book chapter, also the shorter papers in Micro and in the IBM Journal of Research and Development. I think we believe that we have a very good challenge and opportunity for the future, fundamentally creating computer architectures that are data-centric and that can be energy efficient and high performance, computing architectures with minimal data movement that will probably perform computation in many different parts of the system. We have talked today about computing near the cache, computing near the memory, or inside the memory, or using the memory, or using even in the storage, right? Or even in this presentation, I showed you this picture of a prototype from Samsung where they play some processing near memory capability near the CXL memory controller. So yeah, I think that the future is really positive in this direction, and we are going to see more and more real-world processing in memory systems and near data processing systems. So hopefully in a future edition of this tutorial, we will be discussing all these new developments. In the meantime, if you want to learn more, you can go to our website. You can watch many of the talks and courses that we delivered. For example, this long here you can to the YouTube. This or around, and and you missed any of the lectures today, you can come. For sure, we will have also invited lectures as well, and we will likely have new contents and new materials as well. So if you are interested, you will be very welcome to join. And same thing, you can also take a look at our courses. For example, the processing in memory course. These are the links to the fall 2022 edition. But yeah, we are starting the spring 2023 edition probably next week. So yeah, all these materials are available to everyone, and I hope that you enjoy them if you are interested in processing in memory. So that's all for this last lecture. I think we can probably go for a coffee break right now. And yeah, I will be here to introduce the labs in a few minutes, taking 15 minutes or so. You are welcome to join the lab, to have your own hands-on experience, accessing the admin server, programming it. The lab has, I think, plenty of material for more than 2 hours. That's for sure. But the good thing is that the server is going to be available for a few hours after the end of the tutorial. So if you guys want to keep working later this evening or this night in your lab and enjoying the experience, you can do it until the reservation that admin folks have provided finishes. So yeah, thank you everyone for your attention.